coefficients, binary, octal, and hexadecimal. So to convert those binary, octal, hexadecimal numbers to, let's say, to decimal is easy. For example, if I have, So do you know how to convert binary, or octal, or hexadecimal numbers to decimal? The way is the same as how you calculate the value, remember. For example, if I have octal, right? For example, I have 2, 3, 5. This is my octal. Usually you put a subscript, the base in the subscript to indicate which kind of number are you referring to. So to convert that into decimal is 10, right? Base 10. You usually start from the least significant digit, the most right. So 5 times the base 8, and the position is 0. We say position starts from 0, not 1. Okay, you count from the most right then to the most left. So positions are 0, 1, and 2. So those are the position index. Okay, then to convert them into decimal number, you calculate their value. Okay, and it equals to the value in each position times the corresponding weight. Okay, 3 times 8 power 1 plus 2 times 8 power 2. Then this is, you can do the math. Okay, that's how you convert the binary, octal, hexadecimal numbers to decimal. This is an example for octal numbers, converting octal number to decimal number. Similarly, you can do the binary and hexadecimal. The only thing you need to change is the base. You know, if it's a hexadecimal, for example, 2, 3, 5. If this is a hexadecimal number, base 16, so you just change the 8, substitute the 8 with 16, equal 2 times, 18 power 2 plus 3 times 18 power 1 plus 5 times, 16, not 18, 16 power 0. Okay, this is your decimal now. Then you do the math. Okay, so similarly for 1. Okay, so this is, okay, now let's go to the solution. So now you know how to convert binary, octal, and hexadecimal numbers to decimal numbers. So it's the same as calculating the weight, the value. And now let's figure out how to convert decimal numbers to binary, octal, and hexadecimal. So they are, let's start with binary. Binary means you start with the value and divide it by 2. 2 is dependent on the binary, so that's why it's 2. And you find the quotient and the remainder, QR, okay, the first letters. So then quotient is what? 2016. Remainder is 1, right? So you keep going with dividing the current quotient with 2, okay? Then you get the new quotient, and you get a new remainder, new Q, new R. And then 13 over 2 is 6, and this is 1. 6 over 2, quotient is 3, remainder is 0. And 3 over 2, the quotient is 1, remainder is 1. Then 1 over 2, quotient is 0. This is 1. Okay, and another thing you need to remember is that the first, in the end, you collect all the remainders. And the first one is your least significant bit. And the last one is your most significant Oh my God, this is not good. So then you can get 15.3. Sorry, let me try to reconnect the pen, which is so. Okay, let's say what 53. Okay, so decimal number equals to the binary number. So it's then you put 110.101. Oh my God, this is so bad. Let me change the port. Okay, so it's 110101. So this is your binary number. And now you solve this one has been solved. Now let's go to the octal number. So octal number, what you can do is a simpler way is to always start from the binary. You can do the same thing and following the same formula by substituting the 2 with 8, and then you collect all the remainders to get the octal number. And similarly for hexadecimal number, let's do that. But what I meant is that, okay, so we did this in the class, 53 over, I don't know what's wrong with my pen, seems it's not fluent. Okay, 8, then you collect the Q and the R, and the let me see, what if I, is this because of network? Okay, so and we can do the similar thing to get octal representation, which means this over 8. Yeah, I think it's my internet. And let's see. Hold it. Let me do one more thing. Maybe it's my internet that is so not smooth. Let me try it a little bit more. If not, maybe let's change the room. Okay, you get the Q, you get the R. Hold on, let me open the door. Let's see whether the signal is getting better. What if I use my, oh, it's this pen. Oh my God, this pen's quality is not good. Sorry, so, okay, and it seems like it's working now. Let's erase this. You can do the similar thing to get octal and hexadecimal number representations. Oh, now let's omit it. And but the easier way, I mean, it's a matter of habit. If you like that, you can use that way, like 15.3 over 8 equals to. Okay, and you forget about this part. And then you can convert binary to octal number. So what you do is to also always remember to start from the least significant bit. Okay, so then you can start from binary 1, 0, 1. I'm not good at using keyboard. Then you can, okay, you can start from the least significant and combine every 3 together. And every 3 together, then you can get 6, 5. This pen looks like it's dying, but I just got it in the new semester. Let me change it. Six, 5. Okay, so let's try it again. Hold on. Let's try to stop sharing and restart the slide. Looks like maybe it's better now. Okay, so you start from the most right. You combine every digits together, then you are going to get 6, 5. Okay, forget about the pen. Let's talk. Okay, 6, 5. That's your octal number. For hexadecimal number, you combine every 4 in a group. So which is 3, 5 is your octal number. So you put them. That's your hexadecimal number. That's how you get it. And 6, 5 is your octal number. So, okay, for this kind of topic, the requirement is be able to convert one number representation to another. And so do you have any questions?
No, ma'am.
Thank you. So now let's move on to see whether this pen is getting better. Next topic is, okay, Boolean algebra. To use Boolean algebra to simplify a logic expression. And so you have to find the simplest expression. And maybe you are curious why and what are the properties are very commonly used. Okay, so let's start from this problem, and then we talk about all the properties or theorems that you might encounter. So first of all, say this is A plus B naught, then overall naught, right? So then here you need to use De Morgan. Okay, now it's better, right? So next time if it doesn't work, let's reconnect the slides. De Morgan theory. De Morgan theory has 2 forms. One is x plus y naught equal to x naught and y naught. The other form is x and y naught equal to x naught plus y naught. Those are the 2 forms for De Morgan theory, right? So then to solve this problem, first we need to use the De Morgan theory. So let's copy the first 2 terms, A naught B naught plus A naught B C naught. Then this is gives you A naught times, right? Plus becomes times becomes plus, right? That's the 2 rules. And the B naught and the naught is B itself. That's why you get this. Okay, so the first one is from the De Morgan theory, the first step. Then next step, say, let's try this. Say you can say here A naught times B naught This is A naught times B. Then let's combine the two together using combining property. Sorry. This is called, it's combining property. So you get A naught times B naught plus B. Then we copy the middle one, A naught B C naught. Okay, so this equals, this is a single, this one is called a single variable theorem, right? X plus X naught equals 1. Right, this pen is really bad now. Okay, A naught plus A naught. Is this the pen problem and the internet problem? It's a pen problem. This is a, yeah. Okay, so then you can, the first one equals to A naught, right, plus A naught B times C naught. And then you can use what? You can use the, what you call, this property, X plus X, Y. This is called absorption property. X plus X times Y equals to X. This is called absorption. Oh, how can this pen have such a good review in Amazon? The data we've been using it only for 1.5 months, 2 months. Anyway, sorry. And then this equals to A naught. So for Boolean algebra, there are several properties are very commonly used. One is distributive property, means X times Y plus Z equals to X times Y plus X times Z. Okay, then another one is absorption, like this one. And the combining property is also very common. That means if you combine two terms together and the two terms are only different by a single variable, then the final result is copying every variable except the one which doesn't share the value. And what else? And the consensus property. So let's see whether we can write the consensus property means, say, X times Y plus, let's stop share this again and try it. Plus X naught times Z. Say you have X, Y, X naught Z. Then you put the YZ in the middle. YZ in the middle. This equals to the first one plus the last one, ignoring the middle one. That's how you XY times X naught Z. Okay, so that's absorbing consensus property, which is not very common, but sometimes this, especially when you say three variables and three terms, then you may try this, you know. So maybe you were curious, how do I know which one to use? It's really experience. You would have to try different properties to say whether you can make it simpler. So I would say getting familiar with those properties is definitely helpful. Like if you say the not in a term, either multiplication or sum term or product term, then overall it's a not, then you can tell. Definitely here, you have to use De Morgan theory, right? And to simplify things, the theme is to combine things together, right? Sometimes to combine some terms together, you need to expand. So that's why combining property is also very useful. Okay, so now let's look at next one. Okay, here, usually when I say x1, x2, x3, right, two variables. The first one you say is in the most left of the choose table, x1, x2, x3. And then you say, okay, 0, 0, 0 is your M0, 0, 0, 1 is your M1, so on and so forth. Why I say you put L1 on the most left? Because then you know M1 is x2 naught times x2, x1 naught times x3, right? So you know M0, M1, M2 represent what? So that's why I said when I say three variables, I mean the first one I mentioned is on the most left. Or sometimes, for another thing is this. Let me show you. If I say f x1, x2, x3 equals to m1 plus m3. So when I say this, say the first one showed up inside of parentheses is the most left in the choose table. So you know m1 equal to x1 naught, x2 naught times x3, and m3 is x1 naught, x2 times x3. So you want to put this is to avoid confusion when you think, okay, x3, x2, x1, and m0, m1. Usually we don't refer to. So then in the future, when you see those min terms or max terms, you can connect to the right expression, either the product term or the sum term. Let's say Jose has a question. How do you think which property or theorem to use for the last problem? Yeah, so right, that's a good question. As I said, there is no like one sentence I can tell which property. It's like it's like when you say this, right? Then your mind should reflect absorption, this one, because you would say the key is here is what? Is find the similarity. If you want to combine two terms, right? You find a similarity. Okay, for example, here, then I would say A naught is showing up in the two terms. Then I'm thinking about with two same variables, which properties I can apply here. Then absorption I can apply. If you didn't, maybe before you came up with absorption, maybe you are thinking about combining, but combining involves, so that's the key, combining x, y plus x, y naught, and x is shared, y is not shared. So when you say, let's look at, say, if you combine this one with this one, this is because you know this, you can match this to the combining property. So it's more about absorption, you know, your absorption and your how familiar you are with to those properties. So there is no like I take this step, then this step, then this step, then I can find it. So it's more about the experience and being familiar. And maybe let's say this is not a unique way to solve this. Okay, this is not a unique way. I come up with combining the first one and the last one first, right? But maybe you will say, I don't say that, right? So what would happen? Usually, you don't need to start from the exact same steps, but you will also go to the same final expression. So if you apply those theorems or properties at the right time, for example, if I don't know I have to combine, or another thing I would say, what if I, first of all, De Morgan theory, you have to apply it first, because when you have a knot on a humongous stuff, you have to split that, right? You have to apply the not in each of them. Otherwise, you don't know how to use it. So that's why when I say not on either sum term or product term or the combination, then you have to apply De Morgan theory first. Okay, then maybe if you don't combine the first one with the third one first, maybe what if you think, how about I use distributive property, which is x times y plus z equals to x times y. So distributive property means that if you have several product terms or sum terms which share a single variable, then you can extract a single variable outside and then put the rest inside of parentheses. Sorry. That's why I say if you use distributive property first, then you extract a naught. Say every term has a naught, right? This is also a natural way to think. Then you would say, okay, a naught, then times the first one is b naught, right? And the middle one is b times c naught. The last one is b. So this pen is real. Then you can see b times b naught is what? Is 1. Then 1 plus anything equals to 1. So the thing inside of parentheses is 1. Then a naught times 1 equals to a naught. So you can also reach there. That's why I said, in general, the steps you take are not unique. But if you try to what say, so the answer is a naught. Here is the answer. This is your final answer. Answer is a naught. Because if you look at here, a naught times the thing inside of parentheses equals to 1. Then the final thing is a naught times 1 equals to a naught. Okay, then you can say answer is a naught. Or if you take the steps that we initially took, then you are also going to end up with a naught, because a naught plus a naught times b c naught, you can, if you remember this absorption property, means x plus x times y equals to x. Then this tells you if you have two terms which share one part and share the second term, share the whole first term, the whole part of the first one, but has something extra, right? Then the end is equal to the first term. You can ignore the difference. So in other words, you can assume this a naught is x here, b times c naught is y here, then it's equal to x. X is a naught. That's why you can apply the absorption property to get a naught as well. Okay, so is this clear now? Okay.
Yes, ma'am.
Now, thank you, Jose. And now this is the second example. You can use Boolean algebra to simplify a logic expression. And the first thing I say here is, this is example with min terms. Sometimes maybe you simplify something with max terms. So first thing is to make sure what is MIM. That's why I say who is in most left is very critical, you know. So that's why you got those. And so that's why I said don't put x3 in the most left. Why I say this, x1 is left, most left, x3 is most right. Even when I say x1, x2, x3, right? So the first one I mentioned is on the most left. So that let's follow this rule. So that you are very sure about what is M1, you know. Similarly for the rest midterms and the max terms. And now let's look at this example. So let's call the output is F, right? F equals to, let's see how the pen works. Okay, M1 is X1 not, X2 not, X3. And M2 is X1 not, X2 times X3 not. And X3 is X1 not, X2, X3. And X4 is X1 times X2 not, X3 not. And 5 is X1, X2 not, X3. Okay, let's make it simpler. Let me go to the solution we have so we don't need to, because the pen is really not good now. Where is my screen? Let's try it again. Okay, X2, X3. And what else? So we are at M3. Now let's put the X6, X1, X2, X3. Oh, this doesn't work at all. Forget about it. Let's stop sharing. Let's go to the solution and let's talk in here in the solution. So can you see the so now this is your M1, right? M1 plus M2 plus M3, M4, M5, M6, and M7. Now, maybe this looks a little bit scary, right? How am I going to use Boolean algebra to simplify that? Doesn't look like an easy problem. But as we said, you can always try to combining property and absorption property is very, very commonly used. So in other words, it's always intuitive to search for two terms when they are only different by one variable, which is also the basis of K-map, you know, cycling several cells together. And say, then you can tell, okay, if I start with the first one, X1 not, X2 not, X3, right? Then clearly I cannot combine with the second one because X2 is different, X3 is also different. So actually there's nothing you can do by combining the two. So you can only let it be. And then, but then I would say, if I cannot combine the first one with the second one, how about the third one? So you can keep trying, you know? So then you would say, if you combine the first one with the third one, I use the solid line to make the combination clear. Then you will say, okay, X0, X3 are the same, only X2 is different. Then you combine those two together and you use the combining property, right? Then the result gives you X1 not times X3. X2 is different, that's why you can ignore X2. So you get here, X1 not X3. And similarly, you can combine the second one with the third one. Then you would say, okay, the third one has been used twice, right? This is based on the single variable property theorem, X plus X equals to X. That's why every product term or sum term can be reused as many times as needed. Now you combine those two, say, then you will figure out that only X3 has different values. That's why the final result is based on combining property is X1 not times X2. So we get this. And then similarly, you can combine this one with this one, you can get this, and the remaining two. So after do the first round of combining, sorry, we have the 4 simpler terms, right? Because each term is involved with 2 variables only. And now let's check this. X naught times x3, x naught times x2, and x1 times x2 naught. So what caught your eyes is what? You are interested in the second one, third one, the fourth one, because all of them have x1 and x2 only, right? So then you would say, let's say if I want to combine this one, then which one should be combined with, right? x1 not x2. Then you can I do it with this one? No, because those together is exclusive or, so you can not make it simpler. But since you cannot combine this one with this one, then you combine this one with the last one, right? It's combining property again. So after combining x1 naught times x2 and x1 times x2, you can get x2. That's how you get this x2 here. And let's see. So that's how you got x2 here. And then you would say, since x1, x2 are showing up in the 3 terms, though you are ready that you may reuse one term, right? So you combine this one with this one, x2. Then you can combine this one, x1, x2 naught with the last one as well, because they share x1, right? So this gives you x1, okay? So that's why the 3 terms, second one, third one, and fourth one, by using the combining property twice, you end up with x2 plus x1. Now, because the first term has been copied all the time, right? x1, okay, then you are here at this stage. Then you would say, since x1 is showing up in the first term and in the last term, you can combine them together, right? Because that's also natural. x2 is only here, so you know x2, you cannot do anything so far. So you just copy the x2. Then you think about, what if I do something with the first one and the last one? What can I get? Okay, then this is a property that has no name, remember. The property is called x plus x naught y equals to x plus y. And this property is also very common, but the thing is, it doesn't have a name. But I hope you can be familiar with it as well. So this is how I think about when I'm doing the simplification. I will definitely massively use the combining property of absorption and that property I mentioned, x plus x naught times y equals to x plus y. So those properties are very, very common. So you should be sharp, especially on those properties. Then usually you are fine with and the De Morgan theory should also become natural for you. So then I don't think you will have problem with the expression simplification using Boolean algebra. So any questions so far? Okay, let's go back to the, let's see. Let's go back to the slide, So today we will cover as many examples as possible, but even not, that's fine. I will upload it in Blackboard, and all the solutions can be found in the previous exam, in the previous exam. And in your exam, you will solve, there will be 5 problems. So since you will have only 1 hour and 15 minutes to solve the problem, but you, literally speaking, you actually have 1 hour and 25 minutes for your exam. Even I said the last 10 minutes are for you to uploading your solutions, but you 1 hour and 25 minutes are under your control during the exam. So that's why we will have fewer problems than last year. And we will not have multi-choice or true-false problem. We just go to the 5 problems. You solve the 5 problems, then you can submit. Okay, so those examples I chose here are representative ones, means they basically cover all the topics, main topics we discussed so far. And then this one is Venn diagram. Venn diagram, first of all, you have to get the problem here is to use Venn diagram to prove the equality. So maybe I would ask you to use Venn diagram to prove the equality or inequality, right? So first of all, you have to get the universe. If you have 2 variables, you can do your universe like, usually we use rectangular to represent or square to represent uniform. Then you use circles to represent each single variable. And if you have only 1 variable, let's say you have X and Y, that's how you do it. And intersection means and, right? And the union means or. So that's the main thing here. But here, this is the example when you have 2 variables. Now you have 3 variables. How to use Venn diagram to prove something? First, you need to get the Venn diagram of this term, then Venn diagram of this term. Then in the last step, you do the intersection, because in the end, this is AND operation, right? So, okay, this is how you do the 3 variables. Usually you put 1 here. Make sure that each 2 of them have overlapping, okay? So that when you do the OR over the 2 variables, you can find an area, right, to represent that. Okay, so let's say I'm used to put x1, x2, x3 here. But for example, if I don't, it's very flexible. You can put, okay, x2, x3, and x1. This is totally fine, so you can put wherever you want. But the key is to make sure they are all overlapped, they are all partially overlapped. I'm not saying completely overlapped, okay? So the first one is to x1 or x2 or x3. As we said, all the Venn diagram, that is the key. All means union, the union of several variables. And the AND is the intersection. Intersection. Okay, so that's the key. And maybe you are not used to 3 variables. We can always do 2, and then every 2, do 2 variables. Okay, what if I find the x1 plus x2? That's all, right? So that means I'm going to plot the union of x1 and x2, which is this area. Then this is your variable, new variable, right? Then you add the x3. That means the painted area unions x3. So that means you have to plot this area as well. So this result gives you x1 plus x2 plus x3. Okay, that's how you do it. And now let's look at the second one. Second one is, because after you plot this, then it's full. Usually you use 1 Venn diagram, 1 plot to represent 1 term, so it's clearer. Now let's find the x1 plus x2 plus x3 not. Let's find this one. And the thing is that even I say you can put x1, x2, x3, or x2, x3, x1. It's up to you. But once you decide that in the beginning, please don't change across all the problem, In this problem, once you decide I put the x2 on the left, I don't suggest you change. You can do, but it's very confusing if you change. Okay, so then you keep the positions of the 3 variables. Okay, then it's still x2 and x3 and x1. So that's and now remember we did x1 plus x2. Okay, which is the union of x1 and x2, right? Now union x3 naught. What is x3 naught? Let's add the assistance. Let's put x3 naught here. So x1, x2, x3, x1. So this is also x2, x3, and x1. And x3 naught is everything outside of x3, outside of the circle. It's a circle, you know. Everything outside is inside means itself, outside means the complement of the value. So everything outside of this one represents x3 naught, right? Now this is x3 naught. Now I want to get so far here I plotted the x1 plus x2, right? As we said, then plus x3 is it's union. Then what I need to do is to also plot everything outside of x3. Then together. So everything except this area, is x1 plus x2 plus x3 naught. Okay, then the last step is to this one and this one, right? That's the end. End means, remember, end means intersection. Then I need to find the intersection of this one and this one, okay? So then I need to say what's the common area. Intersection means common, right? Common area. What's the common area? Then you can have, let's say, x2, x1, and x3. Maybe then you are not sure which area is common. Sometimes it's hard to see, right? Then you can check each sub-area of the universe. For example, if I check things inside of this area, okay, this is showing up in the top one, is showing up in the bottom one. Okay, then this area is included, right? And now let's look at this area is also shared in top and the bottom figures, right? And the same as this area is also shared. So I can plot it. Hey, this area is also shared, same as this area. But the rest areas are not shared in the top and the bottom plots. So the rest are not included. That's why this is your final, the left-hand side. Left-hand side is, you get this area. And as we said, we know that this is the intersection of x1, x2, x1 is the union of them, means x1 plus x2. So the right-hand side equal to the left-hand side. That's how you can prove the equality. Okay, so that's how to use a Venn diagram to prove that. This is this topic. Let's move a little bit faster. Okay, next is circuit design. Circuit design. So find the simplest POS or SOP. This is involved with K-maps. So K-maps, you should be able to, okay, in the midterm exam, I will not give you 5 variable. 5 variable K-map is actually complicated. So 5 variable K-map in the midterm exam, I will not include that. So you can take it out. And but you should know 2 variable, 3 variable, and 4 variable K-map. 5 you can forget about it for the midterm exam, so we will not test that. It's a little bit complicated. And because it involves 2 4-variable K-maps, right? So that's why it's more complicated. And so this topic is about circuit design. Circuit design means in the end of the day, you have to find the, first of all, you have to put the expression, the function in the K-map. And how to do that? Let's say another thing is POS, find the simplest POS, SOP. POS means you have to circle all the ones in the K-map. And SOP means you circle all the zeros, you know. Okay, so let's look at this example, x1, x2, x3. As we said, when I put give you x1 first, that means in the choose table, x1 is in the most left. Okay, that means x1, x2, x3 are in this order. And I have m2, m3. This means, you know, this symbol means multiplication, continuous multiplication, right? So this means m2 times m3 times m6, you know. Now you need to figure out what are m2, m3, and m6. Those are max terms, right? And how to put them in your K-map. So first of all, let's say, what if I put x1 here, x2, x3 here, right? And then, as we said, if you have one variable, you can put a 0 on top, 1 on bottom. 0, 1 is fine. 1, 0 is also fine, depends. Okay, then 2 variables, usually you can start with 0, 0, 0, 1. Be careful, this is 1, 1, then 1, 0. Okay, so what is a valid K-map depends on whether a K-map is valid or not, depends on whether any 2 neighbors are only different by 1 variable, say 0, 1, 1, 1. It's only different by the first variable. That's why it's a valid K-map, okay? Then you can put here. Then maybe your national question is, where should I put M2? Where is M2? And when I write it in the multiplication or max terms, that means the cells involved related to M2, M3, M6 are zeros, okay? They are zeros. When I have the summation over the mean terms, that means the corresponding cells you have to fill up with ones. Okay, so that's the difference between using SOP and POS expressions. So then you need to figure out what is M2. If you cannot figure out it immediately, I would suggest you go to the choose table first. Okay, so you can say, okay, 0, 0, 0, 0, 0, 1, you know, 0, 1, 0 in this order, 0, 1, 1, then 1, 0, 0, 1, 0, 1, and then 1, 1, 0, 1, 1, 1. Then the corresponding rows are there. You can find the max term. So this is the subscript of the max term is the corresponding row index. And remember, we always start from 0, not 1, okay? So that's why this is M0, this is M1, and this is M2. So your M2, your M3, and let's say this is your M6. And M2, as we said, M2 means X1, 2, 3 are 0, 1, 0, right? So 0, 1, 0 is here. This is M2. So I put a 0 here. And M3, let's say M3 is this row, 0, 1, 1, okay? 0, 1, 1. This is M3. Now M6 is what? 1, 1, 0, okay? 1, 1, 0. This is my M6. So that means the rest are all ones. See here, this is how you can fill up your K-map from the expression, you know. from the expression. If you are not familiar, you can always open your K-map, choose table to see which cells are they referring to. And then next, let's go back to the problem is to design the simplest POS. Simply the POS means I need to cycle those ones, right? Cycle those ones to get a POS expression. So F equal to, that means I need to take care of the 5 ones in the K-map. So you can say, I can cycle those 5, right? Which gives you, remember, when you cycle once, you end up with a product term, and you only keep the variables which share the value, and you ignore the variables which doesn't share the value, right? So that means x1 has different value. This is x1. That's why x1 is out. x3 has different values in different cells. That's why x3 is also out. But x2 is always 0 in all the 4 cells. That's why, okay, you copy x2. Since it's 0, so it's x2 not. And plus, this one has not been included. And this is the prime implicant. That means the biggest cycle you can have. And the resulting product is x1 is the same and it's 1. So, and x3. So that's your final expression, right? That's the logical expression. But here the problem is to design. Design means I need to get the expression. This is step 1, first step. You need to get the expression first. Then you need to give the circuit. Design means you have to give the circuit, okay? Synthesis also means you have to give the circuit in the end. Okay, then you have x2 not, okay, x2 not, x1, x3. Okay, the pain is bad, but the mean here is, oh, this is terrible. You have to get the circuit. Design means in the end you draw the circuit, and but before that, since I'm asking for the simplest, so you have to get the simplest expression. Then based on this expression, you draw the circuit. So x2. That's how you do it. Okay, any questions? Okay. Now let's look at the next one. Next topic is also, okay. It's kind of different. Here, if I want to find the minimum cost, SOP and POS. First of all, you should know how to find POS and SOP both for a given function. But the difference is this part. As we said, when you say the D's, you know, the D means don't care, means those cases will not happen in reality. Then in the K-map, you fill it up with what? With D, you know. And when you do the simplification, when you are doing the cycling, D can be either 0 or 1. But this doesn't mean you can arbitrarily assign 0 or 1 to them. This means that when you want to find the minimum cost SOP, you have to assign some D's to 1 and some D's to 0, you know. But the assignment will be different when you are looking for the simplest POS. So let's look at the, let me see how many examples we have. Okay, timing diagram. Okay, so, okay, not many. Let's go to this problem. So first of all, the key, sorry, step 1, when you say this kind of thing, step 1 is to fill it up in your K-map, you know, in your K-map. And now let's say you have 3 variables. If you put x1 here, x2, x3 here, and you say define 0, 1, define 0, 0, 0, 1, 1, 1, 1, 0. Okay, so Now, as we said, when you say the summation of the midterms, then you fill up the corresponding cells with 1. When you say the multiplication over maxterms, then you fill up the corresponding cells with 0. Okay, so 1, let's figure out the location of 1. 1 is, as I said, if you don't remember, then you go to the choose table, x1, x2, x3. And 0, 0, 0 is M0. This 0, 0, 1 is M1, you know. So you say 1, M1, because this, the first part means M1 plus M4 plus M7, right? Then plus D2 plus D5. Don't care. The locations are in 2 and 5. So M1 is 0, 0, 1 is here. So I put a 1 here. Okay, M1 is finished. Now M4. M4 is 1, 0, 0. Okay, 1, 0, 0. This is M4. So this is 1. Then 7 is 1, 1, 1. So 1, 1, 1. That's why this is 1. Now we have 2 don't cares, you know. So 2 means 0, 1, 0, right? So 0, 1, 0. 0, 1, 0 is here. So you put a D here. Now 5 is 1, 0, 1. So 1, 0, 1 is here. You don't care. Then the rest is 0. Okay. Now that's your K-map. So now this is, let's call it step 1. Step 2 is find the minimum cost, SOP. SOP means I have to circle all the ones, and whether the D's should be circled or not depends on whether it's going to help me to simplify my expression, right? So for example, if now I'm considering this one, so what can I do? I cannot circle it with top one because it's 0. I cannot circle it with the most right. As another thing, remember we said in the K-map, you assume you can fold it left to the right, top to the bottom. So that's why the most top and the most bottom, they are neighbors. Most left and the most right, they are also neighbors. And so, okay, then I check my neighbor on the top. I cannot circle because it's different. It's 0, right? Then I check the other neighbor. It's most right. It's 0. So then I'm thinking, okay, the only choice I have is to circle it with this D. You know, you can circle it with this D. So F equals to circling this D, X1 is 1, X2 is 0, X3 is different, X2 is 0. That's how you get it. Now, now I have to deal with this one, right? So this one, similarly, I can circle it with this D only. Gives you X2 not X3. And then this one, I can also circle it with this D. So, and also with it only. This gives you my expression as X1 times X3. That's your simplest SOP, okay? That's your simplest SOP. Now, we finished the list part. Let's find the last step is step 3 is to find the POS. Simplest POS, okay? The choose table is a little bit mess now, so let's repaint it. X1, X2, X3. Or another thing we can do is change the color of the pen. Okay, let's see this color. So since we want to get POS, we have to circle the zeros, right? So you have this 0, and this 0. And for this 0, I will circle it with this D, right? So that means F equals to, let's say, same one, X3 is, X1 is 0, X3 is 0. So X1 plus X3. Okay, times. Now I have to deal with this 0. This 0, I also combine it with this d, you know, so it's x1 plus x2 naught. Now times I have to deal with this 0. This 0, I also combine those two together. So I can get the last sum term is x2 naught plus x3. You know, so that's how you do it. So in other words, for don't care cases, you circle it with 0 or 1s, first of all, depends on whether you are looking for SOP or POS, right? Second, whether you should circle it or not depends on if I circle my D with 0 or 1, whether I can make the circle bigger. If not, you don't have to. If yes, you should do it, you know. That's the basic line when you have this called incompletely specified function. Incompletely means you have those don't care cases where their inputs will never show up in reality. So that's why it's don't care. Okay, now let's briefly, we have 1 more minute. This is a timing diagram. So as we said, synthesis, eventually you have to design a circuit. So you have to get a synthesis. When I say design a circuit or synthesis, for both of the cases, you have to figure out a circuit in the end. And the simplest means you have to get the minimum cost, you know, SOP or POS. So this is timing diagram. This timing diagram basically gives you the truth table. Based on the truth table, then you can get the K-map or Boolean algebra. Then you can simplify that and then synthesis. So this solution can also be found in last year exam. Okay. Now the last okay, here it is. The last topic is use not and not or gates only. So not and gates only, you have to get the SOP, and not all, you have to get POS, okay? And then, for example, SOP, how are we going to convert? First, you implement using the most direct way, SOP. So you have several sums, right? OR gates. Let's say several OR gates. Then you connect it with the AND gate, right? And now you need to, we're talking about like case 1, case 2. And then you want to use not AND gate. What you can do is that, sorry, this is actually POS. SOP means you have some AND gates first. Let's assume you have 2 AND gates here. Then you end up with OR gate. This is your SOP. SOP direct implementation is this, right? Now you need to use not AND, so you put a bubble here, and a bubble here, and here. And this one equals to not AND. That's how you do it. Similarly, for POS, you directly implement in this way, sum the product, right? Then you put a bubble here, and a bubble here. Because bubble means inversion. 2 inversions cancel each other. And this part, you can substitute it by not all. That's how you do it. And yeah, that's all I want to talk today. And I will upload this with my, let's say, with my notes. So you can, in case you want to check it out right after the class. Okay, so yeah, another thing is that during the exam, please log in your Zoom meeting, okay? So you have to be there. Okay, so any questions?
No, thank you.
Okay, thank you everyone for coming. And let me see whether we have some chat problem.
Thank you, Miss.
Thank you and good luck. Cameras must. No. Okay. The question Lorenzo said, no, you don't need to open your cameras because I know some of you may not have cameras. So no, you don't need to. I trust you. So I know you want to communicate with each other. So you don't need to turn on your camera and just be careful with all the problems and yes, open book, right? Yes. Okay, if you have other things, you can leave. So that's all I want to talk today. And but if you have more questions, I will stay here for a little bit more time. And if you have more questions, you can also come to the office hours 4 to 6 today. Okay. Yes. Yeah. Oh yeah, and the way you submit, yeah, it's like homework. You write it in your own paper, then you turn in. And I know during the exam, usually we are nervous, so that's why. If you can convert everything to PDF, that's awesome. But if not, it's fine. You can. The simplest way for you to do is to take pictures, and then you upload the pictures to the Blackboard. So send everything, upload everything in the Blackboard. Yes. You don't need to type it in the computer. That's not practical, I know. Okay.
Thank you, Miss.
Thank you.